All right, welcome to section 2.2, the limit of a function. So this is where we really start some actual calculus now. So we kind of introduced the idea of limits a little bit in the last section, talking about how we get those 2 points infinitely close together so that we have a second point so that we can create the slope, etc. All right, so now we're really going to see what all that was about. All right, so the limit of a function. To find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. Let's investigate the behavior of the function f defined by f of x equals x squared minus x plus 2 for values of x near 2. So you're going to hear that word a lot today, near some value. The following table gives values of f of x for values of x close to 2. And this is the other thing you're going to hear a bunch of times today, but not equal to 2. When we're calculating limits, the big picture is we're not concerned about what's happening at that specific x value, but what's happening to the function as we approach that x value from either side, either left or right. Okay? All right, so look at this table here and we can visualize what's happening. All right, so this is the function again right here that we're working with, x squared minus x plus 2. So if we plug in a 1, we get a 2. So if we plug in a 1.5, we get that number, 1.8, etc. And what you notice about these x values that we're inputting into the function, these x values are getting closer and closer and closer to x equals 2, but we're not going to be equal to x equals 2. And we can see what's happening. As we put more 9s in this decimal place here after the 1, we can see right here the value that we're getting closer and closer and closer to for the function value. And we can clearly see we're getting close to a 4, right? 3.997. We can imagine as we put more 9s into this x after the decimal, we're going to get just infinitely close to f of x equals 4. All right, so that would be coming in from the left, right? So if we're on a number line, here's 2, right? There's that value, x equals 2. We're coming in from the left with these x values right here. And you'll see, we're going to talk about that more in a bit. We can also see in this part of the table, we're approaching values of x that are approaching x equals 2 from the right. Okay, so the number's bigger than x equals 2, right? And you can see that occurring here. All right, so 3, then we're getting closer to 2, 2.5, 2.2, 2.1, etc., etc., etc. We can see, again, as we get really, 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 really close, infinitely close, right? We could put more zeros here, 1, right? More and more zeros between the 2 and the 1. We can see what's going to happen is that our function value is yet again approaching 4. Okay? So that's the idea of a limit. So this is a graphical representation of the exact table we just looked at right there. So again, terminology as we approach, as x approaches 2 but not equal to 2. What is happening to the function? Well, let's do this. From the left, right? Remember those values on the table we just looked at? The number's smaller than 2, but getting infinitely close to 2. We can follow the graph, right? As these x values approach 2 from the left, we can see our function values are definitely approaching f of x equals 4. And as we approach x equals 2 from the right, again, just like we did on that table above, we can see, just follow the function, right? We can see it's approaching, again, x equals 4. Okay, so that's the general idea of a limit. As we approach a specific x value from either the left or the right, what is happening to the function value? Okay? All right, let's explore that some more. All right, so in fact, it appears that we can make values of our function f of x as close as we like to 4 by taking x sufficiently close to 2. Again, that's what we were just doing, right? Approaching 2 from either side, getting sufficiently close or infinitely close to 2, we could definitely see that the function value was getting infinitely close to 4. So the way we say this now is the limit of the function, this specific function, as x approaches 2 equals 4. Okay, so that's how you say it, and this is the notation. You're going to get used to this notation. We're going to be using it a ton throughout the next chapter and the one after that. Okay, so again, let's look at this notation, talk about what it means. Well, let's go piece by piece here. Let's do this. Let's color code it. All right, so the limit, right? The limit of the function. Of course, there's your function. As x approaches 2 equals 4. Okay? The limit as x approaches 2 of that function equals 4. That's how we say that. Okay, get used to that statement and that notation. So this is the intuitive definition of a limit. I love that word intuitive because the first time I saw this, I said, well, yeah, it's definitely not intuitive. It took a while for me to understand what was happening. But the more you go through this, the more sense it'll make. So here we go. Suppose f of x is defined. So your function is defined when x is near the number a. So one thing to know, this number a is an x value. Okay? Whenever we see this, this is the notation, right? The limit as x approaches a of your function equals L. That a value is an x value. This means that f is defined on some open interval. When we're talking about open intervals here, talking about, again, an interval of x values that contains a except possibly at a itself. Remember we talked about that a minute ago? We said we're really not going to concern ourselves with what's happening at that specific a value, but what's happening to the function as we approach that a value on the x-axis from either the left or the right. Okay, so again, here's the notation. The limit as x approaches a of f of x equals L. L is that limiting value. All right. Okay, limit as x approaches a of that function equals L. If we say that if we can make the values of f of x arbitrarily close or infinitely close to that limiting value L by restricting x to be infinitely close to a on either side of a, and again there's the kicker, right? But not equal to a. We're not going to concern ourselves with what's happening at that a value. All right. So this says that the values of f of x approach that limiting value as x approaches a. In other words, the values of f of x tend to get closer and closer to the number L as x gets closer and closer to a from either side. Again, very important, but not where x equals a. Okay? Again, there's the notation. The limit as x approaches a of your function equals L. Okay? And this is just an alternate notation, but this is the one you will see the most throughout this class and future calculus classes. Notice the phrase, but x not equals a in the definition of the limit. Remember I said that's very important. This means that in finding the limit of f of x as x approaches a, we never consider x equals a. In fact, f of x need not even be defined when x equals a. And we'll go through some examples in just a second here. The only thing that matters is how f is defined near a from either side, left or right. All right, so the figure shows the graphs of 3 functions, and we'll talk about these right now. Okay, so let's look at graph A here. So again, we're going to say, okay, what's happening as we approach x equals a from the left? What value is the function approaching? And we can see definitely approaching L. Okay? Same thing if we come in from the other side here. If we come in from the right, so x value is bigger than a, but approaching a, follow the function. And again, we see the function value is approaching this L, this limiting value. All right, so that one's pretty easy, pretty basic. So here's one. This is where students start getting a little bit confused. But again, let's look at it. And it's important that we remember how your function is defined near that x equals a value, not at that value. Okay? All right, so coming in from the left, approaching x equals a, we follow our function, right? And we definitely see it's approaching, the function value is approaching that L value, where it's interesting because there's actually a hole there, and the function in this case is actually defined at some other value other than L. But again, we don't care what's happening at x equals a. We care what's happening as we approach x equals a. Okay, very important. Oops. Okay, and again, coming in from the right, approaching x equals a, the x value is bigger than a. Again, we don't care what's happening at x equals a, we're following the function, what's happening as we get close to x equals a. And again, we see it's approaching L, the function value is approaching L. Okay? All right. This one's very similar to the one we just did. Notice now there's no definition, right? There's no dot here or anything like that. This function is actually undefined at x equals a. But again, we're not concerned with what's happening at x equals a. So as x approaches a from the left, so x value is less than a, follow the function. Where is it approaching? Again, it's approaching L, that limiting value. Okay, same thing here. Again, approach x equals a from the right, so x value is bigger than a, but getting close to a. Follow the function. Still approaching that L value. Okay, again, not concerning ourselves with what's happening at x equals a. All right, those are important to understand, so please go over those. All right, so let's see. Here's an example. Guess the value of the limit as x approaches 1 of x minus 1 over x squared minus 1. So we really haven't worked with limits yet. If you know how to work with limits, that's fine, but at this point, pretend you don't, all right? So at x equals 1, well, let's see what happens. So here's our function, right? F of x is x minus 1 over x squared minus 1. Well, let's see, what is f of 1 equal to? What happens if we plug a 1 in, right? Because we're approaching 1. Well, let's see what happens if we approach 1. We'd get 1 minus 1, 1 minus 1, which is 0 over 0, which, be careful, that is undefined, right? In other words, there's no y value for an x input of 1 in this case. But what do we know? We can actually remember back, and we did cover examples like this in the previous chapter, right? In other words, let's find the domain of this function. Remember, to find the domain, we take the denominator, set it equal to 0, and then that excludes what values we're allowed to have down there. Okay? All right, so first find the domain. So we know, let's see, this is x squared equals 1. We add 1 to both sides. We square root both sides, so x equals, don't forget, square root both sides, plus or minus 1, right? So actually the domain is x not equal to plus or minus 1. All right? Right, and we know that because we just checked it. If you plug in a 1, actually if you plug in a negative 1 as well, you get 0 in the denominator, which is undefined. All right, so the solution here, so notice that this function is not defined at x equals 1, but again, doesn't matter because when we do limits, we're not concerned with what's happening at x equals a, which is 1 in this case. But that doesn't matter because the definition says we consider values that are close to a but not equal to a. The table below gives values of f of x correct to 6 decimal places for values of x that approach 1 but are not equal to 1. So just like we did in the previous chart up above, right? So x less than 1, in other words, we're coming in from the left. Notice how we're getting infinitely close. We can just keep throwing 9s after that decimal, and we'll see. That's just going to throw more zeros in here. So we can see this limiting value is probably approaching 0.5. But let's check it from the other side. This is coming in from the right. X value is bigger than 1. So 1.5, 1.1, 1.01, etc. And again, we can keep throwing more and more and more zeros in there, and you'll see we're just going to get more and more 9s here. So again, it really looks like we're approaching 0.5. Okay, let's look at that graphically so we can see what happens. So again, here's the function we're working with. We're approaching as x approaches 1, we're looking at the limit of the function. So here we go. This is the function right here. That's that function graphed. So let's follow it, right? As we approach 1 from the left, follow the curve, definitely approaching 0.5, right? The function value approaching 0.5. And as we approach 1 from the right, follow the curve, again, we're approaching a function value of 0.5. Okay, again, notice right there, at x equals 1, this function's undefined. We just did the work to prove that. But that's what we do with the definition of limits. We don't care what is happening with the function at x equals a. We're just concerned with what's happening as we approach from either side. Okay, so based on the charts and the graph, we can definitely safely assume that the limit as x approaches 1 of this function equals 0.5. And you'll see later there's going to be some methods to make a question like this much easier. That'll be in a later section. All right, example 1 is illustrated by the graph of f. So let's change f slightly by giving it the value of 2 when x equals 1. In other words, we're going to make this a piecewise defined functions. Piecewise defined functions are defined in pieces, right? So for any part of this graph, other than x equals 1, we got that curve, the one we just graphed up there. But at x equals 1, we're going to call it 2. All right, so this is that graph now. Here's that piecewise defined, that extra piece they threw in there. But it's still the same limit, right? As x approaches 1, look, here, follow it from the left, from the right. It doesn't matter. It doesn't matter what the function value is. We're still approaching the function value of 0.5. So the limit is still 0.5. Okay? All right, so we keep talking about from the left, from the right. We can just look at one side or the other. We don't have to necessarily look at both sides. All right, so let's see. The function h is defined here piecewise. So h of t equals 0 if t is less than 0, and 1 if t is greater than or equal to 0. So if we look at this, the limit of this function right here, all right, if we're approaching, so less than 0 means from the left, then the function value, or then the limit is definitely going to be 0. Right, because remember, we're not concerned with what's happening at x equals 0. We're concerned about what's happening to the function as we approach 0 from the left. T values smaller than 0. And then look, as we approach from the right of t, right, function value, or values bigger than t, the limit is 1. So you can see the limit does not have to be equal from left or the right, but you'll see later there's a piece of the definition of the limit. So we'll talk about limits from the left, limits from the right, and the limit, okay? And we'll see there's a difference between the three. Okay, so we just talked about that. So we indicate this situation symbolically. So this is important, notation right here. All right, so we read this guy right here. The limit as t approaches 0. So this little minus sign up here means from the left, right? Because think about that. On a number line, negative values are to the left, right? Correct? All right, and here, let's finish reading that. The limit as t approaches 0 from the left of h of t equals 0. So that's that piecewise function we were just looking at. And of course, by now you can probably guess what that little plus sign now means. And of course, that is from the right. So on a number line, positive numbers are to the right. Okay, so limit as t approaches 0 from the right of h of t equals 1. Again, that's talking about this function right here. All right. All right, so this is what we were just talking about, right? So again, watch your notation. Little minus sign right there means from the left. Let's see. So, and of course, I just said the little plus sign on this means from the right. Okay? Okay, so let's go to right here. Now, this is an important definition. Super duper, incredibly important, right? It looks like a lot of gibberish, but we're going to go through it piece by piece here. So I'm just going to read it first, and then I'll explain all the pieces. So, the limit as x approaches a of f of x equals L, if and only if the limit as x approaches a from the left of f of x equals L, and, so and is important here, limit as x approaches a from the right of f of x equals L. Okay? Couple things to this statement here. If and only if, first of all. All right, can't remember if I went over it in this class or not yet, but it's good to hear it again anyway. If and only if, an if and only if statement means that the statement is valid in either direction. In other words, we could say if, oops, that's not what I wanted. Hold on, there we go. If this is true, then all this is true. Or we could say if all this is true, then this is true. Okay, so again, we can make this statement true, well, the statement is true, stated in either direction. Okay, that's important. Okay. All right. So what this is really saying is the limit, this is what I was saying before, the limit exists at x equals a, as x approaches a, if and only if the limit exists and is the same from both sides. Right? They're saying from the left and from the right have to equal some L value. If that's the case, if the limit's the same on the left and the right of some A value, then the limit exists at that A value. Okay? All right, so let's look at that. Let's use that definition so you can see all the mess I made up there on that definition, but it's because it's very, extremely, ridiculously important that you know and understand that. You don't have to write it out symbolically, you just have to understand it. Okay? All right, so let's do this guy here. All right, so A. So we're going to look at this graph and answer these questions here. All right, so the limit as x approaches 2 from the left. All right, so let's see. Here's 2. From the left, we're approaching. Okay, what is the limit? So remember, we follow the curve. That's what we do. So as x approaches 2 here from the left, we're going to follow the curve. What y value are we approaching? We can definitely see we're approaching 3. Again, we don't care that there's a hole there. We don't care that there's a hole there. We don't care that there's function values here. Okay? We're only approaching from the left in this particular part of the problem. Okay? So we can see that limit is 3. Now, letter B here. Limit as x approaches 2 from the right of that function. So from the right, here's 2. Follow the curve from the right. We can see we're definitely approaching a function value of 1. Okay? Hopefully this makes sense. If not, make sure you ask me questions. Email me through the Canvas inbox. All right, so now based on the definition up here that I said was so incredibly important, well, let's see. The limit from the left is 3, the limit from the right is 1, but the statement up above says they need to be equal for the limit to exist. So in other words, this limit does not exist. So DNE does not exist. Okay? If you've ever seen that movie Mean Girls with Lindsay Lohan, remember? She gets all excited. The limit does not exist, right? Well, if you have time, watch that movie. It's funny. All right, moving on. So let's look at another example using the same graph here. Okay, so part D. Limit as x approaches 5, so here's x equals 5 from the left. Okay, so we're going to follow the function from the left as x approaches 5. We can see the function value definitely approaching 2, right? Okay. Now as we approach 5 from the right, so that's part E, right? From the right, follow the function. Again, we see the function value is approaching 2. So guess what that means by that statement above, right? Since the limit from the left and the limit from the right are equal at 2, then the limit exists and is equal to 2 as well. Okay? All right, so this is important stuff. Make sure you're getting it. If not, make sure you're asking questions. All right. All right, as if it's not complicated enough, we can make it more complicated right here by saying we can have limits that go to infinity. All right, well, you've seen these before. You just may not have realized it, but we'll talk about it here in a second. So the intuitive definition of a limit, of an infinite limit, so let f be a function defined on both sides of a, except possibly at a itself. We keep talking about that. Then in this particular case, the limit as x approaches a of f of x equals infinity. Okay? All right. So this is the notation we're going to see. You may see this notation later on, but not in this class. Just a few different ways to state this. But let's look at a picture of what's happening here. So there's our function, right? There's x equals a right here. Okay, so as we approach x equals a from the left, follow the curve, you can see it's going up to infinity. Also in this case, from the left as well, right? Both going to infinity. That's what they're talking about. Another situation is this graph. Again, as we approach a from the left, we can see the function value goes to negative infinity, and also from the right, function value goes to infinity. Okay, so these are just different situations that can occur. So this definition right here is just that example, and this definition is that example, just positive and negative infinity limits. That's all. Okay, but of course we're not limited to one or the other. It could be any combination. So limit as x approaches a from the left can be positive infinity. Limit as x approaches a can be a from the left can be negative infinity as well. And as we approach a from the right, it can be positive infinity or negative infinity as well. Okay, and these are just different examples. So these are good to look at. Okay, let's look at just one of them just to get a basis here. So we're approaching a from the left. Follow the curve, definitely going to positive infinity. Okay? All right, and the other three follow the same logic. All right. All right, and again, just all the different situations that can occur here. If we have any of these 6 situations occurring, then you have a vertical asymptote at x equals a. Okay? All right, so let's look at this here. Example 3. All right, so let's look at this. So let's see. The limit as x approaches 3 from the left. Well, the problem is we can't plug 3 in, right? We'd get a 0 in the denominator. So plugging in won't help us here. But what we can do is use a table, right? So if you want to use your calculator on your TI-83s or 84, hit the y equals button in the top left corner and type the function in. 2x divided by, don't forget parentheses in this case, x minus 3. All right, and then you can use the table function on your calculator. And if you do that, you'll get something that looks like this. So here's the x values, there's the function. All right, so plug in a 2.9. You should get a negative 58. Now, because again, we're approaching 3 from the left. Okay, so value smaller than 3. So now do 2.99. You'll see you get negative 598. Plug in 2.999, you get negative 5998. And that's the cool thing about math, is these cool patterns that come up. So you can pretty much assume 4 nines here, 3 nines here, etc. But let's look what's happening. As we get infinitely close to x equals 3 from the left, that y value, that function value, just gets huge and huger and huger, right? Right? In other words, it approaches, the function value approaches positive infinity. Okay? All right. Let's do this one here. Same function, but now we're approaching 3 from the right. So same thing on your calculator, set up a little table. All right, but let's plug in values from the right. So we'll do 3.1, 3.01, 3.001, and we'll see the pattern. We get a 62, 602, 6002, and of course, you know, however many zeros you put here, that's how many zeros you're going to get in the middle here. Oh, wait, my mistake. Sorry, up above here, that's a negative infinity, right? My mistake. Okay, so big old note here. Fix that. That's supposed to be negative infinity. Okay. All right, sorry. Now below, this bottom one from the right, that is approaching positive infinity. Okay. So based on that, so look at this definition 6 up here. Okay. If at least one of the following statements is true, well, let's see. We've got a limit from the left equaling negative infinity. We've got a limit from the right equal positive infinity. That's 2 out of these 6. But it says we only need 1 anyway. If that's the case, or if any of those 6 are true about this function, which 2 of them are true, that means the equation for your vertical asymptote is that a value. In this case, x equals 3. Remember, x equals 3 is a a vertical line. So if you were to graph this is a very rough sketch. You'd see something like this. So here's x equals 3. We've determined we've got some kind of asymptote here. And based on our work, as we come in from the right, the function goes to positive infinity. And as we come in from the left, the function goes to negative infinity. Either way, we definitely know x equals 3 is a vertical asymptote. Okay. All right. Last question of the day here. So we're going to look at this graph to do this one. All right, so find the vertical asymptotes of f of x equals tangent of x. All right, we can clearly see it on the graph, right? It's those pink lines here, 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 whatever. Tangent goes on forever. We know that, right? With a cycle of pi, with a period of pi. But let's look at it using limit notation. So in other words, we want to know what's the limit as x approaches, let's say pi over 2, from the left, okay, of tangent of x. So let's look at the graph. So here's the graph we're approaching. Now be careful, right? So here's pi over 2. We're approaching from the left. So look up here. Follow the curve from the left. Sorry, that's messy. But you can see that is definitely approaching positive infinity. Okay? So that already makes pi over 2 an asymptote. Let's look at it from the other side. The limit as x approaches pi over 2 from the right of tangent of x. Okay, as we approach pi over 2 from the right, follow the curve. Definitely going to negative infinity. Okay, so either way, this shows us that the vertical, what happened? There we go. Vertical asymptote x equals pi over 2. Okay. All right, there we go. That's it for the day. Make sure you go over these concepts that we covered today. They're extremely important. It's a great basis for the rest of this chapter. Thank you.